马博士你好，非常谢谢各位这么多朋友哦，在这个12月冬天这么冷的晚上还参加我们这个资讯协会的演讲，然后也看到很多这个父母亲带着小孩子来，所以实在是非常感谢你们对资讯协会的帮忙捧场。那资讯协会是2年前才成立的，就希望说办一些跟一般社团不一样的活动。去年我们办了中华民国空军黑猫中队，还有那个 GPS 讲座，也是在这个地方，也是很多熟悉的面孔今天都有再来，那非常谢谢大家。而且我知道今天有些engineer 的朋友本来今天晚上要加班的，像我们陈副总今天晚上要加班，结果他是有 project 要赶的，结果今天还是赶来参加。还有我们的钟吉祥钟博士晚上应该是要去跳排舞的，今天也是要也来参加我们这个演讲会，非常谢谢他。然后希望各位如果等一下方便的话，把你们email 联络地址可以我们留个资料，所以以后我们有机会再继续办类似的活动的话，我们会另外再通知大家。非常感谢大家来，希望大家今天晚上能够非常enjoy今天晚上的演讲，谢谢大家。Steve， 谢谢。
Okay, I'm going to do a brief introduction of our speaker today. It's our great honor as an association to have Professor Ma accepted our invitation. We started the connection in September. Okay, so very appreciated for giving us this opportunity to let everybody to share her great view to the black holes she found in 2011. It surely will promote and further develop our knowledge in astronomy and cosmologies. Many of you might hear the Xindao Chinese radio yesterday. Yeah, it was a very exciting broadcast, and also today, I believe. Dr. Ma set a good example for all our kids, and she is a role model for all of us. Her achievement on the astronomy, along with her route of school years, roused the curiosity and interest of many parents. And I believe you will find the speech tonight will be very educational and also fun. Okay. Now I'm going to do the introduction for Professor Ma. Professor, yeah. Probably for those of you, yeah. You can read it already. Yeah, Professor Ma is right now is a professor of astronomy at UC Berkeley. She was born in Taipei, Taiwan, and also attended Fuxin Xiaoxue, Fuxin School, and also a Taipei First Girl High School, Beiyinü, before moving to U.S. Professor Ma received both her undergraduate and a PhD in MIT. Before joining the faculty of UC Berkeley in 2002, she was a Fairchild postdoctoral fellow at the California CIT, California Institute of Technology, and an assistant and associate professor of physics and astronomy at the University of Pennsylvania. Zhongpei's research interests are specialized in cosmology and extragalactic astronomy. She has studied the property of dark matter and dark energy and cosmic microwave background. Gravitational lensing galaxy formation and evolution, supermassive black holes, and the largest scale structure of universe. And also, Professor Ma got a lot of awards. Those are special ones are listed here. There is a Maria Goper Mayer Award, and also Annie Cannon Award from American Astronomical Society, and also Lindbergh Award of the Distinguished Teaching at the University of Pennsylvania. Okay, I'll let you go through it, and I'm going to only brief a little bit. And Professor Ma is an avid violin player, and began a violin lesson at the age of 4. Yeah, after receiving the first prize in 1983 Taiwan National Violin Competition as a high school student, she continued a parallel study in physics and physics at MIT and music at the New England Conservatory in Boston. She continues to play the violin and enjoys giving an occasional performance with her string quartet. And let's give us our warmest applause to welcome the world-class and beautiful 马中珮教授, the scientist and scholar.
Okay, thank you very much, Steve, and thanks everybody for coming here, as you said, on a very cold night, and I'm sure everybody's busy, and it's especially great to see some young kids here, and I'll be happy to answer questions about physics or music or even education, and I can speak Chinese too, but I feel a little bit more comfortable speaking English about science, but 我会说国语，所以我们等一下可以用国语聊一聊。And don't worry about cosmetologist versus cosmologist. I get that a lot, especially when we sit on the planes, right? People like to chat with each other, and people often ask, "What do you do?" Sometimes I'll say I'm a cosmologist, and then they will go on asking me about the latest Botox. What should I do with my facial? No, I'll pretend I knew something about it. Okay, so I thought I'll spend some time today to talk a little bit about black holes with you. And so to get started, black holes seem to have attracted many people's imagination and attention. And to begin with, so I did a quick Google search of black holes, and of course the things that come off the internet, as you can see, Disney had made movies called The Black Holes, and there's I like this title a lot, A Journey That Begins When Everything Ends. I think this is a great title for a talk. And as you can see, Event Horizon is a recent movie, and so clearly the public really enjoys thinking about black holes. And then I also found maybe the young adults here, I see you smiling. I assume the some parents with young adults at home maybe have to struggle with these games, I suppose. And you need to have a black hole summoner in order to get past some things. Okay? So, and also for people who like pinballs, I just realized that there is a version of pinball, and if you can read here, this says black hole. So you can try to hit it, and there are all sorts of space-time, actually there's a space warpage going on, I think, as the ball travels down here. Okay, so that's pretty popular. So let's talk about first about, so why is a black hole black? Okay, clearly it got its name, Heidong, right? It's a hole that's black. So we can actually pretty simply talk about this property of black hole, the most important property of black hole, by considering a fairly familiar concept called the escape velocity. Okay. And basically what you want to do is escape gravity's fatal attraction. Okay. Gravity is attractive and it can be fatal. Okay. And in a very simple diagram here showing you that on Earth, if you try to launch a satellite or a spacecraft, as we've all learned pretty soon you will learn this in high school, that there is a minimum speed you need to give your rocket in order for it to escape the gravitational pull of the Earth, for example. Okay. So there are some bound orbits here. For example, a lot of communication satellites are on bound orbits about the Earth, so they haven't escaped the Earth's gravitational pull. Okay. But if you wanted to launch a spacecraft to, say, Saturn or Pluto and so on, you need to escape Earth's gravitational pull. Yeah. That's good. That's a little too dark. Maybe a little brighter. Can you make it slightly brighter? Yeah, like that. It's not very important, these. Okay, thank you. But if you want to escape, obviously there's a minimum speed you need to give it, and in very simple formulas, this is the only formula I will show today, okay, is the escape velocity is equal to the square root of 2 times g, which is a constant, the gravitational constant, and m is the mass of the object you're standing on, in this case the Earth, and r is the radius of the object. Okay, so you can plug in these numbers, and you can find that for the Earth, if you try to escape the Earth's gravitational pull, you need to give your rocket a minimum energy velocity, or speed in this case, of 11 kilometers per second. And people are more used to thinking about miles per hour. Of course, we're talking about 27,000 miles per hour, but it's only 11 kilometers per second. Of course, the sun is a lot more massive. It's also bigger. So if you put in the mass and radius of the sun, you can calculate the escape velocity you would need to escape the gravitational pull of the sun. Then that would be a lot bigger, about 1.4 million miles per hour, or 600 approximately kilometers per second. Okay. So that's the concept of escape velocity. Okay. So what does this have to do with black holes? Well, as you can see, what v is depends on the mass and the radius. So you can ask, by the way, I looked up escape velocity on the Google, and again, these buzzwords clearly well loved by Hollywood, and there's a movie called Escape Velocity, maybe you want to check out. I was trying to see what this is like on Netflix, but it doesn't stream, so I'll have to get the actual disc. Probably pretty bad movies, I don't know. Okay. So for the escape velocity, you can now ask, okay, let's fix the mass for now. Say take the Earth. Okay, let's just use that math. But let's assume an alien showed up. Okay, and the alien could squash the Earth, make it denser, make it smaller. Okay, keep squashing it. So this formula tells you that if r gets smaller and smaller, v is going to go bigger and get bigger and bigger. Okay? So let's keep squashing it, right? So the Earth is getting denser and denser and denser. So there is a point at which your escape velocity would approach the speed of light, which is c here. Now we all know that special relativity tells us that nothing can go faster than the speed of light. Okay, and this is not a theoretical statement. This has been proven by various experiments. For example, the famous Michelson-Morley experiment, that nothing goes faster than the speed of light, and the speed of light is a constant. Okay, so since you cannot go beyond speed of light, and speed of light, by the way, is a very large number in miles per hour. Now we're talking about 1 billion. okay, miles per hour. So clearly you need to squash this quite a bit before your v will approach c. But if you reach that limit, then you would need c, speed of light, to escape. But I just said nothing can travel faster than the speed of light. Right? So that means even light, which is a fast-moving thing, cannot escape the gravitational pull. Okay? Now, if even the light cannot escape the gravitational pull, how do we see things? We see things through light. Okay? Therefore, this object will remain dark, black. That's how the black hole got its name. Okay? Let me push this concept slightly forward. Okay? So this is the same formula I just showed. Okay? So now let's set this v to the special number c, speed of light, right? I said that's the extreme limit. Then you can just move these symbols around. I will square both sides, and then this radius went to the left-hand side, so this radius now is 2gm over c squared. So this is a very special radius. Okay? So for an object of a given mass, m, say the Earth, okay, when you make it small enough that the velocity approaches speed of light, this special size, okay, when you reach that limit, is called a Schwarzschild radius. Or you could think of that being the radius of a black hole. Now I put this radius in quotes because black hole really is a point in space. It's a singularity in mathematical terms. Okay, so it doesn't really have a boundary, a surface you can touch. So but we call this a radius of a black hole because it's only an imaginary boundary, but it's a very, very important boundary. Okay, it's a sphere, the size, it indicates the size within which light cannot escape. Okay. And you hear event horizon. Event horizon was used as a movie name. And the size of this radius tells you the size of the event horizon. This is the definition of the event horizon of the black hole. Okay, the region within which even light cannot escape. So in cartoon form, what I'm talking about is really here. Okay, black hole really, as I will say a little bit more later, is a very simple object. People tended to think black holes are so complicated and so hard to understand. Actually, it's very simple. First of all, it's a dot. It's a singularity. Okay, but as I said, there's this imaginary sphere within which you're doomed if you fall into it. Because once you get in here, it will require an escape velocity that's larger than the speed of light to get out, and you can't do that, so you can't get out. Okay, as long as you stay outside of this boundary, you're safe. Okay, so you could have imagine you could have a rocket just hovering above the event horizon. Okay, going around and around. It requires amazing engines to do that. Okay, it's not feasible, but just imagine for now. Then you could actually watch what happens to the black hole, and you wouldn't get sucked in. Okay, so that's the event horizon. Okay. So then let's come back to this formula one more time. Okay. So this formula is telling us that for a given mass, right, g is a constant, c is a constant. So for a given mass, there's a corresponding size for the black hole, the radius, the event horizon. So this equation, then let's check out, what is the number for some familiar masses? Okay. So one thing you do know, right, from this simple equation is the larger m is, the larger the radius is. And it goes proportionally. So more massive black holes have larger event horizons. Okay. So let's put in some numbers, right? We talked about Earth. Earth, of course, is not a black hole. But if we could somehow crush it, okay, then you can ask, for Earth mass black hole, what is the size of the event horizon? It's 1 inch. Okay, so if you're away from 1 inch, away from the black hole, you can escape. Okay, just don't get within 1 inch of the Earth-size black hole. But of course, when you put in the sun, okay, this tells you it grows. So the short radius of the sun is about 3 kilometers. That's about 2 miles. Okay, so that's, right, it's between here and, I don't know, 880 or something. Okay, so if you were able to squash the sun into a singularity, okay, then you would not want to get within 2 miles of the center of that, the black hole. And today I'll be, later on, I'll just speak briefly about the record-breaking black holes we found just about a year ago. And those black holes are about the, some of the most massive black holes known. And there we are talking about black holes. Again, the black hole is a point, but its mass is what we were trying to measure. Okay. And we found the mass is about 10 billion times that of the sun. Okay, 10 billion solar masses. And this is a very simple formula. Just multiply this by 10 billion, you get the answer. Okay? So but if you change into reasonable familiar numbers, then the event horizon, or the sphere of no return, the short radius that you wouldn't want to get into for a 10 billion solar mass black hole, is about 5 times the size of the solar system. And by solar system here, I'm using the distance between here and Pluto, you know, about 40 astronomical units. So 5 times as big as that. Okay. So here was a publicity slide we used last year. This is an actual image of a galaxy which we studied. I'll talk a bit more. These very monster, big, massive black holes tended to live at the very centers of galaxies. Okay. But if you blow up here, imagine this were the black hole, okay, and this boundary is the event horizon. Then if you were to draw the size of the solar system in here, this is the solar system. This is just to indicate that the size of the event horizon is approximately 5 times the size of the solar system. Okay, so it's kind of big, but it's not huge, right? It depends on what you compare it to. Okay, so let me turn to another. So now that we've talked about why black holes are black, okay, and we've talked about this mass and this sphere that you would not want to get close to, let's turn to a little bit of astrophysics. Okay, let's think about, so where have we found black holes? Okay, why do we think they're out there? Okay, so I'd like to talk about 2 kinds of black holes today. Okay, the first kind is actually the more familiar kind. Stars are a ball of gas that's fusing, going under thermonuclear fusion at the core, turning hydrogen into helium. Those are the normal stars. And our sun is a very ordinary middle-aged star. Okay. But stars are like people. They were born one day, and then they age. They go through the midlife crisis, like our sun right now, which is about 4.6 billion years old. And given another 5 billion years, what's sustaining the star right now, which is this fusion at the core, eventually hydrogen is going to get used up. Right? Hydrogen is all going to turn into helium. And helium can turn to heavier elements. Eventually that process that's giving out energy would stop. When that stops, a star starts to die. Okay, so stars will age and it will eventually die. Now there are 3 graveyards of stars that we know for astronomers. You know, ordinary stars like our sun, which is everywhere. There are trillions and trillions of them. Our mass is not big enough to die as a black hole. Okay, black hole is one possibility. So we think our star sun will die as what's so-called a white dwarf. Okay. However, there are stars that are more massive than our sun right now. Okay, there are fewer of them out there, but there are some of them. So when their masses are about 10 times, roughly, okay, that of the sun, a bigger star, they have more fuel to burn, but they burn them faster. So they're the extravagant version of, you know, an ordinary people. So they spend really fast. They got a lot of money, but they spend even faster. So they live a short life, but their life is spectacular. Okay, massive stars have a spectacular death too. So when they die, they don't become a white dwarf. They become either a neutron star or a black hole after a extraordinary explosion called a supernova explosion. Okay. So we know that the death of massive stars should result in a black hole. So right now, the best evidence for the stellar mass, sort of a few, sort of tens of solar masses black hole, is this system called Cygnus X1. So this is an artist, obviously, a drawing of this system. But we have a lot of astronomical data of this system. So this is a binary star system in our own galaxy. It's called Cygnus because it's in the constellation Cygnus. Of course, it's it's somewhere out there in our galaxy. X1 because it gives out copious amount of X-ray emission, and we have X-ray satellites above the atmosphere that can see it. Okay, and X-rays, as you know, are extremely energetic. Okay, so only very, very strong gravitationally pulled system can emit X-ray to accelerate things to such a high speed to give out X-rays. So what we think Cygnus X1 is a binary star system, okay, where you have a pretty ordinary big star here still burning hydrogen into helium, but its companion had already died and became a black hole. Okay. And so you can't see the black hole, but there is a lot of mass being dumped. These are two stars orbiting each other. Okay, so a lot of mass is being channeled onto the black hole and feeding it. Okay, black holes will start to emit a lot of radiation right outside its event horizon when you pour a lot of gas onto it. Okay, so we see a lot of radiation from this source. And because it's a binary system, we can we get a lot of data because they're orbiting each other, so we can do Doppler measurements, right? How fast it's moving towards you and away from you. So this is an extremely well-studied system. And right now, the latest measurements indicate that the mass that's sitting here and that's giving out a lot of the emission is about 14.8 times the mass of the sun. Okay, about 15 solar masses. So this, and there are some other similar systems that are known. The masses may be not as precisely measured, but these are pretty common systems in the galaxy, for example. So indicating that these are sites of stellar graveyards. Okay, graveyards are very massive stars. However, this is not the type of black holes we've been studying, and we don't call these monsters. Okay, so now let me turn to the second type of black holes that we know about. So let's scale things to a much larger scale now. Okay. So let's think about galaxies. Okay, so we live in a galaxy called the Milky Way. Our galaxy has probably about 10 billion stars in it. It's shaped like sort of like a pizza. Okay, it's flattened, and this is an actual image now. Okay, this is an infrared image of the pizza we live in. Okay. And as much as we would like to think that we were at the center of the universe, okay, as you know, right, for more than 1,000 years we thought we were at the center of the universe and everything rotated about us. Makes sense, right? Come on, you look around the sky, it's orbiting about us. We kept getting thrown out. Okay, so we first realized that the Earth is not the center of the solar system, right? We're orbiting about the sun. Where is the sun? Sorry, folks. The sun is not at the center of our Milky Way. We're really off from the center of the pizza. Okay, we're sort of like an olive living at the very edge of the pizza. And this is a beautiful image. Since we're at the edge, we can look into the disk of our galaxy. And you see the reddish thing tended to be dust, silicon grains that like to radiate in the infrared. And you're seeing basically star dust and gas, light from our own Milky Way. Okay, and Moreover, which will not be a topic of today's talk, but that's something I've studied a lot, is a galaxy you think of, being made of stars, gas, dust, right? Stuff that we know of. But in fact, our many current measurements indicate that surrounding a galaxy is this huge sphere of stuff called dark matter that you can't see. But the mass in the dark matter is at least 10 times, if not 100 times more than the luminous matter, the stuff you can see. So I just want you to imagine here, okay, in addition to the stuff astronomers can actually see, we infer that there is a huge dark matter halo surrounding each galaxy. Okay. But what I would like to talk about today is at the very center of each galaxy. And there appears to be a black hole lurking. Okay. So how do we know about that? So let me zoom in here. Okay. So this is another infrared image taken by the world's largest telescope, the Keck telescope on top of Mauna Kea in Hawaii. And we UC have 40% of the time access to these two telescopes. And this is an actual image towards the galactic center, the center of our own galaxy. And it has a name, Sagittarius A star. Okay, don't worry about the jargon, but some of you probably have. Who is Sagittarius? You probably know, right? Your signs, right? I think it's around this month, isn't it? It's December, right? So I don't know how many of you have seen the Sagittarius constellation on the sky. Okay, it's beautiful out there. It's next to Scorpion, and it looks kind of wiggly. And look toward there and think. Just remember, that's where our galactic center is. And that's what this beautiful picture shows. Okay. So these are actual stars toward the galactic center. Okay. So let me zoom in more. So right now, the best evidence for a supermassive black hole, okay, these black holes that are not the end state of a massive star, but I mean millions to billions of solar masses. Okay. The best evidence is in our own galaxy. It's this object in here, which of course you can't see. Okay. The arrow is pointing to nothing, right? There's a lot of radio emission, X-ray emission coming in from here. But what people are able to do, and this is an incredible measurement done by some of our colleagues, is they can zoom into the very center. And because our galactic center is relatively close, it's about 25,000 light years away. It sounds big, but for the big universe, it's actually fairly close. People are able to actually track, you can't see the black hole, right, by definition. So if you want to infer the existence of a black hole, you got to look at things orbiting around it to see how fast they are going. Okay. So what people have been able to measure, the star indicates where the galactic center is. And this is the actual position of about 16 stars traveling over that time period. I'll show this again. Sorry. So that's an animation. Okay, so you can see the actual orbits from 1995 to last year of some of the stars. And this is not an animation, this is actual measurements. So what's remarkable is you see, right, this S2 has almost completed an orbit, almost like, right, some asteroid going around the sun, right? And this S16, for example, it was happily going around and suddenly turned around, right, to move. It got deflected. Why would it do it? If a star were left alone to travel, it would just move. It would just go like that. So the fact that, right, so everybody seems to be orbiting about something, right? This is like, it's turning. Some of these orbits haven't completed yet because its orbit is longer than, 16 years. Okay? But people are continually measuring these orbits. So what you could do is, using the combination of these orbits, simple computer program, you can infer who is pulling on these stars, making them turn around. Okay? And the common solution turned out to be a 4 million solar mass black hole at the center, at the location of the star. Okay, this is really amazing measurement, and it's a consistent solution. That is, assuming a 4 million solar mass thing there, you can explain the orbits of all these stars around them. Okay. Now, I can go into more details, but I don't want to get into that right now, is how do you know that's a black hole? Okay. That's pretty hard to prove, except right now, since these stars are getting so extraordinarily close to this point, you can limit now. You can say there's at least 4 million solar masses within a tiny, tiny volume. Okay? The closer you get to it, the tighter you have this constraint. So, of course, we as astrophysicists, we love coming up with new theories. So there is no lack of attempts to try to explain this central object as something other than a black hole. Okay. For example, could you hide a collection of 4 million solar mass stars or something really dim, or strange stars? People cook up with all sorts of scenario. Ironically, black hole right now is the simplest explanation for the motion of these stars. Again, if you were to take away this 4 million solar mass thing at the center, there's no reason for these stars to be deflected at all. They should just all move on a very, very smooth trajectory. Okay, so that's thus far, and this is a fairly painstaking measurement, and they are still continuing to follow these stars to refine their measurement. So the 4 million solar mass is quite well determined now. So let me give you some other examples of where in the universe where we think there are also black holes lurking. Okay, I don't want to go into the details here, but here are just some pretty pictures of some other galaxies. Okay, in this case, M87 is a giant elliptical galaxy. It's not like our Milky Way, which is a disk, looking like a pizza, but rather there's sort of two major classes of galaxies based on their morphology. One is the disky kind, like our Milky Way and the Andromeda. The other is called elliptical galaxies. They tended to be enormous, and they tended to look like a spheroid. They're not flattened like a disk. Okay, and a lot of us study why are they such and such, how do these galaxies form and so on. But M87 is a giant elliptical galaxy, much bigger than our own galaxy. And at its center, we can see very energetic jets of gas being shot out. Okay, usually these are all indicates there's a very active nucleus. We call it active galactic nucleus, or sometimes we use the word quasars. You may have heard of quasars. It's a brand of electronics, I think. Okay, but quasars, we can see them to very, very far, billions and billions of light years away, because they're so energetic. And quasars are believed to be powered, the radiation is believed to be powered by the stuff that's accreted onto a central black hole. Okay, so these are just some other examples of where we think there are black holes lurking. And just like stars, okay, most of the stars in a galaxy actually are not like our sun, which is a single star. In fact, more than 50% of the stars live in binary systems, like Cygnus X1 you saw. Okay, they like to have a companion. Similarly, there are a few sources right now we know, not so many, that we suspect there could be a binary black hole. And here I'm talking about binary supermassive black hole, two monsters orbiting each other. Okay, this is another image of this galaxy called NGC 6240. This is just a normal optical image of the galaxy, but if you zoom into the very center, these pictures are taken by the X-ray Chandra satellite by NASA. And it shows two emissions, two clumps of very energetic gas. This is a few thousand light years apart, okay, which is quite close for astronomical distances, separations. And the current interpretation is at the center of each one of here lives a supermassive black hole that's giving out this radiation. Okay? And we believe probably these two black holes are bound, and eventually, if they lose enough of their orbital energy, they could actually coalesce and merge to form a bigger black hole. Okay. Okay, so I've just given you some pretty pictures of where we think the supermassive black holes live. Okay. So in terms of our own work, I just want to spend 5 minutes on it. Okay, so again, black holes are black. So how do we find black holes? Well, if it's black, it looks like a hole, I say it's a black hole. Okay, sure. So what we set out to do about 4 or 5 years ago was to study, like M87, okay, the nearby, some of the biggest galaxies, elliptical galaxies, and to look at its very, very center, okay, where the light is brightest, and attempting to measure, again, you can't see the black hole, but we try to measure the speed of the stars orbiting around the very center. Okay, you can't track each star individually like in our Galactic Center, but you can do it statistically. You can look at a bunch of stars together and try to measure how fast they're going to infer the gravitational pull of the central mass. Okay. So one example is this famous cluster of galaxies called the Coma cluster. Okay. Again, this concept of cluster is quite important in cosmology. Okay, galaxies, right? Oh, by the way, here, so if you look at each dot, it's a galaxy. Okay, this is a humongous. You may think each dot is a star. Okay, it's not like the previous picture I showed you of the Galactic Center. This is over millions and millions of light years on a scale. Okay, and each fuzzy blob is an elliptical galaxy on this plot. Each one has probably a 10 billion to up to 1 trillion stars in it. Okay, the universe is quite big. And so each one, and that is a foreground star. Anything with spikes, okay, because of diffraction, this is a foreground star. But these fuzzy, cute little blobs, each one is a galaxy. Now galaxies, we know a lot of them, millions, millions, millions of them on the sky. And they are sort of like people. You can ask, how are people distributed on the Earth? Right? You take a satellite picture of the night view of the Earth. Some parts are completely dark. San Jose is brightly lit, right? So just like people, so people love to cluster in cities and so on. But for different reasons, galaxies also like to cluster. Okay, in that case, it's due to gravitational pull. So galaxies are not randomly distributed on the sky. It's not like a Poisson distribution or something. They are distinctly clustered. So this is a famous cluster of galaxies. So it's a cluster. It doesn't quite look like a cluster to you, but if I show you a larger scale of the universe, this is quite dense. Okay? And so this is a famous cluster called Coma cluster, and it has, we can identify hundreds and hundreds of galaxies that live in this cluster, physically associated with each other. So this cluster is about 300 million light years away. And you can see two big fuzz balls here. And these are the two brightest galaxies in the Coma cluster. And the brightest one, the biggest one in this cluster, which tended to anchor the potential of this group, is NGC 4889. This is just a zoom in of this. It doesn't look like it much of anything, right? It's just a lot of light. But just to keep the perspective, we're talking about 1 trillion stars you're looking at. Okay, this is light you're seeing from about 1 trillion, 10 to the 12th solar masses of stuff out there. Okay, this is a very, very big thing. So what we did was, we wanted to see, does Coma's brightest cluster host a black hole at the center? You can try to stare at this plot and try to see if you see a black hole. Of course, you're never going to see it. Okay. So the key is not to do the imaging, but to get the speed, kinematic, the star velocity. Could these stars at the center be orbiting so fast that they're being pulled by a black hole? Okay. So that's what we attempted to do. Now, in order to study a galaxy at its very center at this distance, we had to use, and the reason this couldn't have been done until now is because these galaxies are fairly distant, so they're faint. So in order to collect enough light, you need a big telescope. Unfortunately, this one won't quite work. Sorry, yeah, but maybe some other maybe the black hole in this room, yeah. Okay, so we use the largest telescopes available to us. I mean, on Earth, really. So this is the twin, the Keck telescopes I mentioned earlier, and we also use the Gemini, which is a U.S. government-funded rather than privately funded telescope. It's an 8-meter telescope. So these are the two largest telescopes in the world. By 10 meters, I'm referring to the diameter of the mirror, right? So, I mean, think about this, half the size of this room, right? It's a very large mirror. And also, we need a very good instrument. So in addition to the mirror, in the back of these fancy telescopes, there are very, very fancy cameras or spectrographs that can disperse light to tell us about the intensity versus frequency to get a spectrum. Okay, so we use a combination of these instruments, and it's sort of, you have to apply for telescope time to get allocation to observe these objects. And of course, you're lucky to get the time, then you have to be even luckier for the weather to be good, which is fairly annoying. This is already one of the two best sites on Earth. This is atop Mauna Kea on the Big Island. So most of the time you go up, I don't know how many people have gone there. If you go to the Big Island, you can see these little white domes at the very top, and two of them are the Keck telescopes, and Gemini's there too. Okay, so these are beautiful sites, but still it could rain there, it could snow there, or the seeing, when the disturbance is too big, you can't really do what you want to do. And we require very, very good conditioning in order to see the stars. So that's why it took us a number of years to get enough data. Okay. So let me, rather than going through the details, let me just show one more slide to explain why these black holes are relatively difficult to detect. Okay. So again, the idea here is, this is the Keck telescope on Earth, and we're looking at Coma cluster, okay, which is about 300 million light years away. But what we needed to do is not to study this galaxy as a whole, but to pierce at the very, very center. And what I'm talking about is, we need to look at the stars at basically the inner 1,000 light years or so. Okay, think about inner 1,000 light years. 1,000 light years, again, sounds like a big number. Okay. But it's actually quite small, right? 1,000 light years at a distance of 300 million light years, right? It's a tiny, tiny thing, okay? So let me draw an analogy. So what we need to do, we need to measure how fast these stars are moving using spectrographs. So the analogy would be, that I could think of, would be a little bit like shrink the 300 million light years to the distance between the Bay Area and Los Angeles, okay? And we can use this telescope here. Now let's try to look down towards Los Angeles. So what we're trying to do is basically like looking at Yo-Yo Ma performing in the Disney Hall, okay, from here. But we would like to measure how fast his fingers are moving using the telescope. Okay, so given this great distance, clearly you've got to have very, very good instruments and very good condition in order to do that. So we were able to, so far we've published 5 black hole masses, ranging from 1 billion up to 10 billion solar masses. And our goal really is not to break the record and then stop or anything. Our goal really is just to study. We would like to understand these most massive black holes, okay? And what they have to do with the galaxies they live in. Okay, a very interesting finding so far had been, as I said, these black holes tended to live at the very center of each galaxy. Okay, the more galaxies we look at, the more black holes we find. And more interestingly, the bigger the galaxy is, the bigger the black hole seems to be at the center. Okay, in cartoon form, this is sort of a very exciting correlation we're seeing right now, which is if you plot the mass of the black hole you measure using these methods I mentioned, versus don't worry about the central bulge or something. Think about this being the mass of the galaxy. Okay. Basically, the Milky Way is a tiny one, right? We have a 4 million solar mass black hole. It's about down here. Okay, so it's 4 million, it's about here. And you go to these more massive elliptical galaxies, right? We found 10 billion solar mass black holes. So that's actually above this plot here. And these are some of the biggest galaxies. So somehow these little black holes know about this huge environment they live in. Okay, and how do they come about? Clearly has something to do with how the galaxies evolve as a whole. Okay, so tracking this cosmic history of black hole growth and galaxy growth is one of the very active field of research right now, and that's what some of the things we are working on. How do you explain this growth? It's a little bit like, you draw the growth chart of a child, right? You can see the taller they grow, the more massive they grow, with a significant scatter about the mean relation. Okay, so we're trying to get more data, and we're working on theoretical models for these objects. So I'd like to now just to spend a few more minutes, okay, back to the black holes in general, to talk about a few myths about black holes, okay, and to try to dispel them. Okay. So one is people tended to think, right, and I contributed to that by giving the title of the talk as Monster Black Holes, as if they're evil or something. Okay. So one question we get a lot is, oh, you just told me there's a black hole at the center of our galaxy. Should we worry about being sucked in? Okay, so are they cosmic vacuum cleaners? Well, so again, it's yes or no, okay, depending on where you are. So back to the escape velocity, the event horizon concept I gave you earlier, right? You have to be near the event horizon, and if you fall within it, then you can never get out. Okay. But if you are far away from that boundary, right, and if that size of event horizon, as I told you, depended on the mass of the black hole, right? For Earth mass is only an inch. For the sun is 2 miles. For our giant black holes is 5 times of the solar system, right? But if you're far away from that, for example, our solar system, right? I just told you is 25,000 light years from that 4 million solar mass black hole. Okay. In this case, we don't care, right? Because, as you know, Newton's law, m is m. Mass, mass is sitting far away there. Then our orbit would be the same. So to have another imaginary scenario, if we were to now replace the sun, okay, keep its mass, but let's squash it into a black hole. Okay, so it became a solar mass black hole. Would it change Earth's orbit? Okay, no. The event horizon, I said, is only 2 miles. Okay, so as long as you're not near that, for anything outside of it, Newton's law tells you all you care is how much mass there is. Okay, whether it's condensed to a singularity or spread out as the sun, it actually doesn't matter. Okay, the only worry is it will be kind of cold, of course, if you replace the sun by a black hole. Okay. Of course, if you were to replace the center, the sun, okay, by a 10 billion solar mass black hole at the location of the sun, then, of course, life will become interesting, right? Because then the Earth's orbit would be within the event horizon. And I would hate to speculate what would happen to us. Okay, so basically you have to be very close to the black holes to worry about being sucked in. And that's exactly how we see such energetic particles and gas that's emitting energy that we can see. But when you're far away, you're okay. Another myth is black holes are complicated and they only exist in science fictions. And they certainly do exist in science fictions. Okay? And just to say a few things. First of all, black holes are predicted to exist in general relativity. More specifically, black hole is a mathematical solution, okay, to the Einstein equation, which is the foundation of general relativity. The Einstein equation just describes you've got a blob of something here, some mass. How would it warp space-time around it? Okay, it's just an equation, kind of like the equation I wrote down, which is much more complicated. Okay, but it's just an equation, so you can calculate, you can find the solutions to the equation. And Carl Schwarzschild was the one to find that black hole is one solution. There are many solutions. Black hole is a allowed solution to the Einstein equation. So mathematically, it can exist. Okay, and then, as I said, black holes, right, general relativity has been rumored to be understood by, 3 people in the universe, or 12.5 people or something? Okay. It is not true. You can all go and understand general relativity, okay? It's a standard graduate level physics class. But one thing about black hole is it's actually extraordinarily simple in the sense that imagine how many variables we need to specify to uniquely determine Steve. 3, that's right, simple man, right. So for a black hole, if you specify its mass, which we've talked about a lot. If you specify spin, a black hole can spin like a ball. Okay? And a black hole can have an electric charge. Okay, I won't go into the details here. Once you specify these 3 quantities, a black hole is completely specified. Another way to say it is 2 black holes with identical 3 numbers are indistinguishable. Okay? A lot simpler than people, right? Okay. And as I mentioned earlier, ironically, black hole is weird as it sounds, as fascinating, strange as it appears, is actually the simplest explanation for many observations. For example, the orbits of the stars near our galactic center I show you. Okay, you can cook up alternative theories that require even more strange things than black holes, like stars made of strange quarks or weird things. Okay, so in some ways, black holes are actually the simplest thing. Okay, so the last thing, I want to just return to my title, black holes are monsters. Well, why don't we wait until December 21st? Okay, it's coming. We should have scheduled the talk on that day. Or I think it depends on your point of view. I think black holes could be your friends. Okay. I think it's really fascinating. And just to end the talk, I would like to show you. So this is, we took this off iPhone of our 4-year-old son, this last year when he was 3 in his preschool.